introduction, Professor Ali. Uh, so I'll start by presenting sharing my screen, and I hope that I'm audible. And let me see my screen. Hopefully, will be visible as well. Second. So
Yes, sir,
sometimes
you are audible and your screen is also visible.
sometimes we have network issues here. So in
Yes,
case that happens, let me know. I'll switch my network.
it's all fine, sir.
So okay, good. So slideshow. All right. So today's lecture, although this is a workshop, I must warn you that it is more of a research talk. But I will try and go through the details of the methodology to some extent, a little more than I would for research talk perhaps. But it is really going to be about this topic that we have been studying for the last 5-6 years in our group. And the work has been mainly done by Dr. Ramiz Bahadur Shah, who just received a PhD from IIT Bombay this year. And a very active collaborator in this project is Professor Rajneesh Bharadwaj from Department of Mechanical Engineering, IIT Bombay. I of course know that today he's going to also present his lecture on the methodology. So that way I don't have to, in fact, hopefully go through too much of that in detail, because he's really, I think, much more active in methodology compared to myself. Okay, so today we'll be focusing on a very simple problem, in fact, of vortex-induced vibrations of a cylinder. In fact, this kind of problem now you can solve it in almost any software. I mean, including, I think we were just having a chat about ANSYS with Dr. Furkan, and I think we can solve this in pretty much anything now with many different methods. So the point of this talk is really going to be in terms of trying to look at energy extraction from vortex-induced vibrations. Okay, so first of all, what is vortex-induced vibrations? In case you don't already know, so you can just think of a bluff body like a cylinder, which is attached to a spring and damper in parallel. And then there is a flow, there's a uniform flow which is going across the cylinder. And because of this uniform flow, there is, of course, shear layers which are developing on both sides of the cylinder, and that causes vortex roll-up and vortex shedding, periodic vortex shedding, which can then, of course, lead to periodic lift forces to form on the cylinder, to act on the cylinder. Okay. Now, of course, whenever you have this kind of a forcing from the flow, you can then try to ask the question that, well, can we extract the energy that is being sort of input by the flow into the cylinder, and what is the maximum amount of energy extraction efficiency that we can hope to achieve. Okay. Now, this kind of idea has been around for a while, and in fact, in 2008, Bernie Thas's group in University of Michigan, they managed to basically fabricate this kind of generator, which is called as Vives. And in Vives, they basically have a cylinder which is being attached to essentially servo motors and to to electromagnets. And what that setup does is that what they manage to do is they manage to actually control the damping as well as the spring constant through these servo motors, and that way they are actually able to really explore a very large range of parameters for the system, okay, without actually physically changing springs or physically changing the damping. And they managed to show, in fact, that you can actually generate up to about 20-30% of the energy from the fluid in this way, okay, which is a very large number, in fact. And the effect of spring nonlinearity is also of a lot of interest, and one of the first papers that I've seen where they have looked at this kind of spring nonlinearity is in a paper by Makowski and Williamson in 2013. This is published in Physics of Fluids, where they really systematically changed the nonlinearity of the spring, and they found that there was a larger energy extraction efficiency as well as a larger range of flow over which this extraction occurs. Now, even without going to the next few slides, we can imagine that when the fluid is flowing across the cylinder and the vortex is shedding with some sort of a vortex shedding frequency, then you will expect to see a larger amplitude if this vortex shedding frequency is similar, if not similar to the natural frequency of the spring. Okay. And so that is really the hope, that you will get a somewhat large range of flow rates where you can actually get large amplitudes. And of course, when you get larger amplitudes of oscillation, larger lift because of larger lift forces, then you can of course try to extract also more energy from the fluid. Okay, so right. So these are some of the important parameters in the problem. One is the mass ratio. So mass ratio is nothing but, you can say that it's the density. It's actually the mass of the solid divided by the mass of the fluid displaced by the solid. Okay, so that means it is m star is ms in divided by ms is the structure mass, and then this is pi by 4 rho d square. Okay, if this is a solid cylinder, then this is the mass ratio, and of course it will be proportional to the density ratio in general, density between the solid and the air. The other important output here is actually the displacement amplitude, which is small a naught. Natural frequency, or the linearized natural frequency, is also very important. Okay, when I say linearized, I'm of course implying that when your spring becomes non-linear, then there needs to be some way to characterize the natural frequency. So one of the ways to do it is to look at the very, very small oscillations around the equilibrium state, and that is the natural frequency based on those very, very small oscillations is the linearized natural frequency, which is this omega s. Okay, and that is of course under root k by ms, which is where k is the linearized spring constant. Then you have the vortex shedding frequency, which is there because of just if the cylinder is stationary, then there is a characteristic vortex shedding frequency, which you're going to call as omega f, and there is a characteristic Strouhal number based on that, which is simply the non-dimensional vortex shedding frequency. Okay, and so that is non-dimensionalized with respect to the velocity, the inflow velocity, and the diameter of the cylinder. Typically, the Strouhal number is 0.2 over a fairly large range of Reynolds numbers. And then you can also look at something called as the reduced velocity. Now, reduced velocity is very important. Basically, it is the velocity of the inflow velocity of the fluid, incident velocity of the fluid, normalized with respect to the spring constant. Okay, and basically you can rewrite this as 1 by Strouhal number times omega f by omega s. Okay, and so omega f, remember, it is the characteristic vortex shedding frequency, and omega s is the natural frequency of the spring, linearized natural frequency of the spring. So when these two are similar or the same, then as you can imagine, the 1 by st, since it is about 0.2, you can imagine that when UR is around 5, then you will get very large oscillations, because at that point it means that omega f by omega s is about 1, and so then you will get very large oscillations in your cylinder. Definitely you will get very large oscillations in your cylinder, because you are sort of trying to force it at its resonant frequency. Okay, so this is pretty basic stuff which you would expect from this system. But then something very interesting happens in vortex-induced vibrations of bluff bodies, which is called as a lock-in phenomenon. Okay, and this again very basic, which is very old kind of phenomenon, which is very, very well documented. But here is the interesting thing. So suppose I look at the, of course, so let's first look at, if I do a simple experiment where I just measure the amplitude of oscillation of the cylinder. So A by D is the non-dimensional amplitude of the cylinder oscillation, and let's say I'm fixing my mass ratio to 10. and I have got the reduced velocity on the x-axis. Okay, so reduced velocity, remember, it is basically a proxy for the vortex shedding frequency divided by the structure frequency, or the natural frequency of the structure. Okay, linearized natural frequency of the structure. This result I'm showing is for a linear spring. That means that the structure basically has the same natural frequency no matter what amplitude you have. Okay, so in linear springs, the natural frequency is independent of the amplitude of oscillation. So you can see that if my reduced velocity goes to 5, the amplitude seems to be the highest. But then I do get pretty significant region over which I have large amplitude oscillations. Okay, and there is in fact a lot of work which is done on understanding these different branches, upper branch, lower branch, and all that, which I'm not going to get into. Okay, that is very specific. Again, very specific type of studies which are done for that. So this study at least is not really focused so much on those things. But one thing you can see is that not only at UR5, but it actually goes almost up to UR10, where you see UR is a reduced velocity, okay, where you see the amplitudes to be high. Okay, so what is going on here? So if you look at the ratio of the structure frequency F to the linearized, or to the natural frequency Fs, okay, then what you see is that in this range where the amplitude is large, it seems like F by Fs is or F by Fs naught is almost equal to 1. Okay, but then outside this range, you see that all the points seem to be outside the range where the amplitude is sort of high. So basically, in the low amplitude region, you can see that these points, they seem to be lying on what is called as a Struhal line. Okay, so F by Fs equals to 1 is simply, you can say that it is simply it is very, so okay, these points you can see they're not exactly 1, but they are lying close to 1, let's say around 1.3 or 1.4, and this would essentially correspond to the oscillation frequency of the solid being very close to its natural frequency. Okay, and whereas if they are lying on this straight line, then it would be the oscillation frequency of the solid lying very close to the vortex shedding frequency. So in fact, what happens here is very interesting, which is that not only the oscillation frequency of the solid, but even the vortex shedding frequency, it actually starts to lock in with the natural frequency of the structure. Okay, and that means that it's sort of getting pulled away. The vortex shedding frequency is sort of getting pulled away from its characteristic shedding frequency, and it is therefore basically locking in with the natural frequency of the structure. And on the other hand, when my reduced velocity is very far from this number 5, so let us say it goes to 15 or something, then it is the structure which is actually locking in with the vortex shedding frequency. Okay, so basically there are these two different scenarios of lock-in. One in which you can say that the fluid locks in with the structure or with the natural frequency of the structure, and that happens very close to when your vortex shedding or when your reduced velocity is somewhat close to 5. And on the other hand, when it's far from 5, you can say that it is the solid or the structure which is actually locking in with the vortex shedding. Okay. Now when you go for very large mass ratios, there is actually a very simple piece of analysis which shows that your vortex shedding frequency, and basically in this case your vortex shedding frequency will actually lock in with the natural frequency of the structure. Okay, so whenever you have large amplitude oscillations, then this situation will actually happen when your mass ratio is high. So when your mass ratio becomes, let's say, 20 or higher typically, then what you can expect is that these points which are lying on this Struhal line, they will actually not correspond to very large amplitude oscillations, and only points which are lying on this line, they are actually going to correspond to very large amplitude oscillations. Now, how does this scenario change in the presence of naturals, in the presence of nonlinear springs? Well, the first thing that we can say is that, well, clearly the natural frequency of this structure, if the spring is nonlinear, it will be almost, you can say that it will not really depend so much. It will rather depend a lot on the amplitude of oscillation. Okay. And so in the presence of nonlinear spring, we can sort of expect that the lock-in chart that we are seeing here. So this chart is often called as the lock-in chart. You can actually replace this natural frequency of the of the linear spring with the natural frequency of the nonlinear spring, which will definitely depend on the amplitude itself. Okay. So basically, you can see that there is some amplitude here, very large amplitude, which is happening, let's say at UR5 and then different amplitudes at different URs. So natural frequency itself can actually start to depend on the amplitude itself. So then that, of course, makes the whole situation a little more tricky. Okay. So we will see what is the sort of what happens when you have nonlinear springs. So the presence of nonlinear spring, this has been in fact studied extensively. Like I said, especially in the recent past, many groups have been actually studying this. So if you look at the force displacement type of curve, okay, then what you can do is you can try to make, for example, you can try to make the restoring force. This is actually restoring force, so that's why it's not going up. It's not having a positive slope. It's a negative slope here. But this restoring force, if it is linear with respect to the displacement y, then what you can imagine is that it will just be minus ky. Okay, but then if you have a restoring force which is nonlinear, then you can see that it will actually have it can have a cubic term in y, or it can have a higher order term in y. Okay, so this is what was actually studied by McCoskey and Williamson, and later on Wang et al. Also published some papers published a paper in Ocean Engineering on the same topic, where they got very similar results. But what was seen was that when your spring becomes nonlinear, okay, so basically this lambda value, it actually sort of controls this nonlinearity coefficient here with respect to the linear coefficient. Then you can actually start to get large amplitude oscillations over a much larger range of Reynolds number. Okay, so this black curve is when this bold curve is when your spring is completely linear. Okay, lambda equals to 0. But then when your spring becomes very highly nonlinear, and this is mainly for hardening springs, then you can see that this actually becomes very, very, the Reynolds number over which your large amplitude oscillations take place can be very, very wide. Okay, and several groups have been actually seeing that. Okay, with different types of setups, they have been seeing that when your spring becomes nonlinear here, then you start to get a wider range of velocities over which your flow is, over which you start to get vortex-induced vibrations. And that's, of course, really good from the perspective of energy harvesting, right? Because for energy harvesting, you want large oscillations. And from those large oscillations only, you can actually try to get some of the energy. Okay, so what we are going to do is we are going to look at, we basically ended up studying bistable springs. Okay, so what are bistable springs? So if you look at the spring potential, okay, so remember that spring potential, if you take if you basically take the negative of the derivative of the spring potential with respect to the displacement, then you get the spring force. Okay, so if you have, let's say, a linear spring, then your spring potential is simply a quadratic curve. If you have cubic spring, it is like this. You have some y to the power of 4. If you have a bistable spring, then this is the third one is actually in this table. The third row is actually your bistable spring. So when you have a bistable spring, then it will have two stable points. That means that my spring potential, it will actually have a minima at these two stable points, and it will actually be unstable in the middle. Okay, so when the cylinder oscillates, you can say that it is going through some kind of a snap through action. Okay, it is if it is able to harvest very little amount of energy from the flow, then it sort of stays within one potential well. It oscillates within some potential well. But then if it is able to harvest more energy, it is able to snap through from one well to another well and go back and forth like this. Okay, so that is basically what a bistable spring potential looks like. And of course, if you keep varying these parameters of the bistable spring, this K1 and K3, if you keep varying that, then in that case, you will actually get different types of bistable springs. So you can see that you can actually adjust the spacing between these spring potential minima, and you can also adjust the depth of the minima here with respect to the zero potential. Okay, so these are basically the two things that you can adjust here. Okay, so you can imagine that if your depth becomes more, keeping this distance between these minima as a constant, then you will actually have a more and more stiffer spring around this stable point. And on the other hand, if your depth is more, again, this similar kind of thing can happen. Okay, and on the other hand, if you start to increase the distance between these two minima, then what you can imagine is that you will need pretty large amplitude oscillations for the cylinder to jump from here to here. Okay, so in all of this, I have tried to sort of crystallize what are the important parameters of this spring. So one is your y naught is your ratio between, basically the square root of the ratio between these spring constants, but actually it's not really, it's really, okay, it is important actually. This y naught is actually basically giving you the location of the stable point with respect to y equal to 0. There is a y critical, which means that this is the distance where your potential again becomes 0. Okay, so this is the distance from y equal to 0 where the potential again becomes 0. Okay, so that means that if you have an oscillation in vacuum, then you just need to go beyond this y critical amplitude for your cylinder to oscillate between these two wells. The k here is actually the linearized natural frequency of the spring. Okay, and basically rather linearized spring constant around y equals to y0. Okay, so that means it is the linearized spring constant around the stable point. And you can also then write down these non-dimensional versions of the interval distance, which is beta. So beta is basically the magnitude of y naught divided by the diameter of the cylinder. Okay, that is, so this beta is actually what we will see now going forward. And y critical is the non-dimensional threshold distance beyond which you will start to get double well oscillations. Okay, and so that's it. So mainly, in fact, you need to really, just going forward, you need to really sort of remember that the beta, whenever we say beta, it is a non-dimensional distance between the spring potential. Okay, so first thing that you can do is you can try to ask the question that, well, what is the natural frequency if my cylinder is undergoing an oscillation of some non-dimensional amplitude a naught? Okay, because remember that the natural frequency omega s here, it is only for very, very small oscillations around the stable point. Okay, now if my oscillations start to increase, then in fact the way even in the presence of vacuum, the way my the y versus time, basically, that can actually be pretty complicated function. It will no longer be a harmonic function, because this is a this is a nonlinear spring, right? So what we did was, again, the details of this, you can look up in our paper, but basically what we did was we characterized the natural frequency in terms of the maximum amplitude of oscillation, as well as the interval distance. Okay, in fact, you can show by dimensional analysis that your non-dimensional natural frequency, so this is omega n by omega f, it is actually going to be having this kind of a form. Okay, so basically here I have non-dimensionalized with respect to the vortex shedding frequency, which is why you will actually get the reduced velocity and Strouhal number as a non-dimensional numbers here. And this non-dimensional function, which is important here, is actually a function of a naught by beta. Okay, and so this non-dimensional function is it is going to have two different forms depending on whether my cylinder is undergoing single well oscillations or whether it is undergoing multi or double well oscillations. Okay, and these two forms we have actually mentioned it here. Okay, so there's this one has some kind of a, you can see that it's actually depending like the square of the a naught by beta here, and then in this case it is actually depending on somewhat more complicated function, in fact, okay, for the single well oscillations. Okay, but what you can see is that as my a naught by beta it increases, so again a naught by beta is the amplitude divided by the interval separation. So as this increases, you can see that the natural frequency omega n divided by the linearized natural frequency, it also increases. Okay, so then that makes sense, because as my distance increases, my potential actually becomes steeper and steeper, and my spring in general, on the average, the spring is becoming more and more stiffer. And obviously a stiffer spring should give you a much higher natural frequency. Okay, so that's basically what we are seeing here. Okay, so okay, so these are the two different regimes in which we have characterized the natural frequency. Okay, so first thing that we did was we used something called as a Wake Oscillator Model to characterize this vortex-induced vibration due to bistable springs. Okay, so Wake Oscillator Model is a very simple model which basically structural engineers, they have come up with this tool, okay, where you don't have to do a CFD. You just solve for a 2 degree of freedom kind of problem, where the first degree of freedom is your non-dimensional displacement y. Okay, so y is small y is basically capital Y by d. So this is non-dimensional, simply the non-dimensional displacement of the cylinder. And Q is the non-dimensional vortex lift force, which is basically a non-dimensional, you can say that it is the lift coefficient, normalized lift coefficient, you can say. Okay, and so there are only 2 degrees of freedom. Now, if you look at these equations closely, what you will see is that the first equation, it simply has the inertia term, it has a damping term in which you have structure damping coefficient and a fluid damping coefficient. You have the mass ratio here, okay, and you also have this delta, which is nothing but your linearized natural frequency divided by your vortex shedding frequency. Okay, so this is basically nothing but a proxy for reduced velocity, you can see. And then this part here, it is actually nothing but the spring potential coming into the picture, the restoring force due to spring potential. On the right hand side, you have a forcing term, which is there because of your lift forces. Okay, so this Q is nothing but the non-dimensional lift force. The equation for the lift force is quite interesting. So it is not simply a sinusoidal lift force. This lift force, it is having its own equation. So you can see that it's a second order equation in time. Okay, and this damping term Q dot, it actually has this form epsilon times Q square minus 1. So when Q is less than 1, okay, when the amplitude of the lift force is less than 1, then it actually leads to a pumping of energy into the system. Okay, so basically this leads to an unstable type of damping. Okay, and there is also forcing on the right hand side from the cylinder, but what you can see is that even if the cylinder has no forcing, there's no sort of forcing because of the movement of the cylinder, even then this will actually reach a limit cycle where it will have a some limit cycle with a vortex shedding frequency, okay, and with some normalized amplitude of lift force equal to 1. Okay, so these are two coupled equations that we are solving, and it's a very, very crude type of model, but it is still, you can get a lot of insights from it. Okay. So what we found is, as expected, so this is my y equal to 0. If this is what a linear spring displacement versus time kind of plot looks like. So it is, we start with a large amplitude and we let it go, and you can see that it is sort of just giving a nice sinusoidal type of behavior as far as the y versus t goes. For the bistable spring, if my beta is large, beta is around 0.2. Okay, beta, remember, is an interval distance, normalized interval distance. Then in that case, we get only single well oscillations, where you will get your y oscillating around a negative mean value. And if you have a very small value of beta, 0.05, then your y actually, it seems to be oscillating around 0 in that case. Okay, so now it is clearly undergoing double well oscillations. Okay, and so these purple lines, these are actually the critical thresholds. Okay, so this means that if you go beyond this critical threshold, you get double well oscillations. And these dotted red lines, these are in fact showing the minimum of the spring potential in y. Okay, so these are different types of oscillations that you can get. You can get basically double well oscillations, or you can get single well oscillations. Okay, so Rami's first thing that he did was, he looked at, okay, if I look at the maximum oscillation amplitude A naught, I can actually plot it as I can sort of represent it as a contour plot over a parameter space given by M star and UR. Okay. So I apologize for all the noise coming. Unfortunately, a lot of construction going on beside my office. So I hope that's not causing too much of an issue. Okay. So, so your M star is there on the x-axis and UR is there on the y-axis. And the shading, basically darker shading basically implies that you have a large oscillation amplitude. So you can see that when your M star becomes large for linear springs, then your large oscillation amplitudes happen only over a somewhat narrow range in the reduced velocity. Okay, between, I would say, 4 and 7 or so, you see some kind of oscillation happening. Otherwise, in these white regions, there is no oscillation amplitude. Okay, so it tells me that for large mass ratios especially, the range of oscillation amplitude is very limited as far as the UR is concerned. Now, when you go for bistable springs, if your beta is small, what you find is that your amplitude of oscillation can be large over a fairly large range in reduced velocity, and it in fact seems to be going up with reduced velocity. Okay. If your interval separation goes up even more, so beta equals to 0.25 compared to 0.05, beta equals to 0.25 has a much larger interval separation. And in that case, you can see that again, for large mass ratios, you have a limited range of reduced velocity over which your oscillations are occurring. Okay, so basically, it seems like with bistable springs, I can actually go for very small values of beta, and I can get a fairly large range of reduced velocities over which the oscillation is occurring. Okay, and okay, this is a slightly busy plot, but basically what we are looking at is, at the top, what we are looking at is the power spectral density of your y versus t, or y dot versus t actually. Okay, which is where the shading or these actually the contour plot has not been shown here, but basically the magnitude of the shading is telling me that large energy content is present at this particular frequency, and the frequency has been plotted. Normalized frequency for the power spectral density has been plotted on the y-axis, and on the x-axis you have the reduced velocity. Okay, so these are actually all, so let's say 2, 4, 6, 8, 10, 12, these are all different simulations which are happening, and I'm getting one power spectral density curve for each of these reduced velocities, and the omega has been normalized with respect to the natural frequency of vortex, the characteristic vortex shooting frequency rather. Okay. So omega equal to 1 means that let's say that I have a peak at omega equals to 1. For example, in your linear spring, I can see that there's a peak here and here, which is at low and very high UR. You can see that the peak in the PSD seems to be at omega equals to 1, which means that the oscillation frequency, it's basically having a peak around the vortex shading frequency. Okay, around basically on the Struhal line. It's following on the Struhal line in this case. Okay, so this, by the way, this omega, it's the, so I should say that, yeah, this is basically representing the natural frequency of the oscillation. This contour plot is the natural frequency. Sorry, actually, my bad. So the contour plot is in fact the FFT of the lift force, and these boxes, these are actually the natural frequency of the spring, and these asterisks actually, in fact, so my bad. So the asterisks are in fact the structure frequency. Okay, they are the peaks of the structure frequency. Okay, and what you can see is that the peaks of the structure frequency, they are matching the peaks of they are matching the natural frequency, and they are also managing to get the fluid frequency to lock in with them over this narrow range in UR. And outside of this, you can see that the structure frequency, it no longer is matching the natural frequency, and rather it chooses to lock in with the fluid frequency, characteristic vortex shading frequency. So you can see that therefore there is a narrow range of reduced velocity over which you get a large amplitude in oscillation in Y. On the other hand, when you look at these bistable springs, then there seems to be a very large range in the reduced velocity, where my natural frequency, vortex shading frequency, structure frequency, everything seems to match. Okay, and there seems to be a very large range over which that is happening, especially for smaller beta values. So this is for again, I apologize. I think this is caption is not there, but this is for beta equals to 0.05. On the other hand, when you go for larger beta, then again the range over which the natural frequency, structure frequency, fluid, the characteristic vortex shading frequency, all these are actually matching. That range actually again goes down, and you again get this large amplitude oscillations over a much narrower range in the UR. Okay. If you plot everything with respect to, if you make the lock-in plot with UR equivalent instead of UR, so here UR equivalent is based on the amplitude dependent natural frequency. So this is the reduced velocity, which is based on the amplitude dependent natural frequency, and you plot that on the x-axis, then you will actually see that all the points, they start to fall on each other. Okay, so that is nice. So it means that whatever is going on is somewhat universal. So lock-in that is going on is somewhat universal. Okay, and basically everything seems to be locking in within the same range of UR equivalent. Okay, but obviously they are not locking in the same range of UR. Okay, UR is based on natural on the linearized natural frequency. Okay, so that lock-in does not happen actually in the same range in UR. Rather, it is happening over the same range in UR equivalent. Okay, so what we did was we came up with, we wanted to come up with some idea about why is it true that for bistable springs, or in general for spring nonlinearity, why is it true that you start to get a larger range of reduced velocity over which you see lock-in happening. Okay, so what we did was we looked at the equation for the cylinder displacement, and we then really managed to derive a budget for the cycle averaged kinetic energy. So this averaging here, it's actually a cycle averaging. When you do that, then what happens is that the inertia term and the spring term, they actually drop out. Okay, because spring and inertia, they cannot really create or dissipate energy. Okay, so energy can be only created or dissipated by the vortex shading forces and by the fluid or structure damping. Okay, so therefore we only have the net energy dissipation due to the structure or fluid damping, balancing out the net energy dissipation, net energy production due to the vortex shading forces. Okay, And if I now assume that the oscillations are more or less harmonic, okay, which is a bit of an assumption when your spring is nonlinear, but let us say that we are basically looking at the fundamental mode of the oscillation. And we say that, okay, we are basically getting harmonic oscillations in the displacement as well as in the lift force. And so in that case, of course, there'll also be a phase difference between the lift force and the displacement. Then in that case, you can actually come up with a constraint between the amplitude of oscillation and the frequency of oscillation. Okay, and this constraint is coming purely based on energy conservation type of principles. Okay, it's a very, very simple energy budget that we wrote down to derive this. So if you look at this very closely, the C, gamma, M, these are all constants. Q naught and this psi, these are essentially some functions of A naught and omega. Okay, so if we know this functions of these functions Q naught and psi, then we can actually get these constraints. So now what is this Q naught and psi? So we can actually flip it around and we can say that, well, basically if I oscillate the cylinder with a certain amplitude and frequency, then the non-dimensional amplitude of the lift force and the non-dimensional phase difference which I will get in the lift force will be my Q naught and psi. Okay, so what we did was we took this Wake Oscillator model, we carried out that exercise where we just did a sweep over different amplitudes and frequencies of structure oscillations, and we got a model for our Q naught and psi, and we basically did a little bit of fitting of polynomials, and also we took a little bit of hint from this paper by Fascinetti 2004 as to how this phase angle should be, and we managed to come up with a very simple sort of algebraic model for these functions Q naught and psi. And once you do that, you can actually get the equilibrium constraint by looking at the zero isocontour of this function. Basically, this is the equilibrium constraint that I showed. The left-hand side minus right-hand side, when you look at it and it goes to zero, then you get the equilibrium constraint. So for linear springs, so the interesting thing is that your equilibrium constraint, it actually doesn't have the spring coming to the picture anywhere. Okay, it is actually purely, you can say you are using purely it's purely it depends on the properties of your vortex shedding, and it is also given by the energy, your energy balance basically. Okay, so this is how your equilibrium constraint looks like, and really the punchline here is that when you have linear springs, then if you plot your natural frequency curves for your linear springs, then they are basically these vertical curves on this plane. Okay, so basically your natural frequency, it doesn't depend on the amplitude. So your natural frequency versus amplitude curve for linear springs are these straight lines, and they vary with the reduced velocity like this, and they intersect this equilibrium constraint curve, this red curve, over a very narrow range in the frequency line, or basically equivalently over the reduced velocity. On the other hand, when you have bistable springs, then because these natural frequency curves actually have a slope in this plane, therefore there is a much larger range in reduced velocity over which they are actually able to intersect this equilibrium constraint curve. So the equilibrium constraint curve is the same, but the natural frequency curves, they change, and therefore you get a much wider range in the reduced velocity over which these oscillations are actually seen. Okay, so this graph is, again, because I'm running out of time, so I will try to actually wrap it up in the next 5 minutes or so. So I will skip this, basically the same kind of thing. So again, in our paper, we have shown that, you can actually really write down this very nice theoretical estimate of what is the range of natural frequency over which the lock-in happens. And when you go for smaller and smaller values of beta, you will get a larger and larger range for which you start to see this kind of lock-in, range of velocity over which you see it lock-in. That's the basic thing. And it is all based on this equilibrium constraint kind of thing. Okay, so does this equilibrium constraint, can you actually show it from simulation? So we actually looked at Wake Oscillator Model simulations. We looked at the A0 versus omega coming out of these simulations. They actually do seem to be falling on some sort of a curve, this onion-shaped curve. Okay, so it seems like at least the Wake Oscillator model does show this kind of equilibrium constraint to exist. This slide I will skip, but basically we showed that the theory and the Wake Oscillator model simulations, they agree with each other qualitatively as far as the prediction of the amplitudes go. And we also conducted some CFD simulations. So in these CFD simulations, we basically just solve for Navier-Stokes equation, and we solve for Newton's law for the structure, and your Fy is simply the net force which is acting from the fluid onto the solid. This is what the mesh looks like, and your delta min, the smallest grid size is about 0.015, so it's about less than 2% of the cylinder diameter. This is the time stepping, there's a fixed time step that we used, and it's about 385 to 257 grid points. One thing I want to add is that when you solve these type of equations, you have to be very careful about time stepping. So we used a Verlet time step because that actually really conserves the elastic energy of the solid. Okay, otherwise you will start to see a decay happening in the solid oscillations. And yeah, I want to just add that this is basically based on the ghost cell based inverse boundary method, which Professor Rajneesh Bhardwaj actually, he works on that method a lot. And so we used a code which is based on that method. We did lots of validation here, and we also looked at the grid convergence. So we are getting a grid convergence, which is about the order of accuracy is, let's say, somewhere between 1 and 2. It's closer to 2. It's closer to being quadratic in terms of grid convergence. And we did lots of CFD simulations with this. The bottom line is that even with the CFD simulations, fully resolved CFD simulations, we did see a nice collapse of data points on this A0 versus omega type of curve. And we did also see that when you plot A0 versus the reduced velocity, then you see a larger and larger lock-in range when your value of beta goes down. So here you can see that beta goes to 0.1, your lock-in range is higher in the UR. So you can see that over UR, you are getting from about 3 to 20 is your lock-in range. Okay, and this is the typical vortex shedding patterns that we observed. We typically observe either a 2-row or a simple 1-row 2S type of vortex shedding pattern. Okay, and this 2-row pattern we see typically when the cylinder oscillations are very large. One important thing is that the vortex shedding patterns, so here for example we're looking at linear spring and bistable spring. These patterns seem to be depending a lot on the amplitude of oscillation and rather than the spring type. Okay, and that means that basically how it is going from one extremum to another extremum doesn't seem to matter as much as the actual extremum it has, and of course the frequency which it is oscillating at. Okay, so it seems to be pretty universal with respect to these two parameters. Now what we also looked at is we looked at energy extraction, and again I don't have much time to look at this to talk about this, but this is basically this work is now under review, where we looked at the energy extraction efficiency, and what we found was that again with bistable springs you get a very large range over which you can extract energy, and in fact if you systematically vary this Skopf Griffin number, then there is a sweet point in Skopf Griffin number where you can actually get about 20 to 22% of energy extraction efficiency with a bistable spring of beta equals to 0.1. Okay, and moreover we can actually explain this again with our model. So with our equilibrium constraint model. So when you start having any kind of structural damping, then we show that you can actually get this extra term here. Okay, and this extra term, it depends on the Skopf Griffin number by UR. And you can therefore parameterize your equilibrium constraint curves with different values of this SG by UR. Okay, and then you can try to see that where is the lock-in occurring with the natural frequency curves. And what you will find, in fact, is that you can, in fact, show, again, there's not much time to go into that, but you can, in fact, show that when you start having this kind of bistable springs, then there is a larger range over which you are actually getting this lock-in, because for different values of UR, you actually are skipping over to different curves. Okay, and that leads to an especially larger value of the energy extraction efficiency. Okay, and again, I'm not going to really go through this in much detail, but yeah, you can actually see equilibrium constraint curves coming out of the simulations itself. And we again simplified our theory a bit, and we actually came up with very nice expressions, analytical expressions for what should be the efficiency of the energy extraction efficiency and the amplitude of oscillation in the presence of bistable springs. Okay, and yeah, we showed that there was a pretty decent match between the theory and this kind of CFD simulations over a wide range of beta and reduced velocities. Okay, so I'm going to end here because we are basically out of time. But basically, we are able to show, or what we observe is that when you have spring nonlinearity, then there is a larger range of reduced velocity over which you start to get high amplitude oscillations. And the reason it happens is that when you have nonlinear springs, as you increase your flow rate, your spring is able to, your cylinder is able to increase its amplitude, and it's able to therefore make the spring more stiffer effectively. Okay, because especially if you have hardening springs, then as your amplitude increases, your spring becomes stiffer, and your natural frequency actually changes. Okay, so for nonlinear springs, they can adapt their natural frequency as per the flow rate, whereas linear springs, they are not able to do that. Okay, that is the basic reason why you see that for nonlinear springs, you have a larger range over which you have this kind of your energy extraction efficiency as well as large amplitudes. But the more what we have done is we have gone somewhat deeper than that, and we have tried to build this theoretical construct on that. And so yeah, you're welcome to, of course, take a look